Hello guys, welcome back to my channel. And I am making this video because I wanted to complete um, the notion that I started on my first video. Basically, the first video being Introduction to Gamma Digamma. The first video where I made this YouTube channel a brand sort of thing. And there I had decided to show you that the digamma of 1 is negative Euler-Mascheroni constant, but let me be honest, I tried and tried back last year, but I couldn't do it. But now there has been a change. There has been drastic improvement, evolution in my mathematical skills. I'm not bragging, but I felt this was a significant milestone in terms of where I was before and where I am right now. So that's why, without using any series for the digamma function, I wanted to prove that the digamma of 1 is minus Euler-Mascheroni constant. So let's get started, and I hope you'll like this video and appreciate the continuation that I wanted to do. So if at this point you don't know what first video I'm talking about, please check out the video. I've probably added a card about now. Check out that first video, and you'll get to know that in that video we had to basically find the value of gamma prime of 1, or the first derivative of gamma with respect to uh, the parameter n at 1. So if you define gamma of n to be integral from 0 to infinity of e raised to negative x times x to the n minus 1 dx, then derivative with respect to n of gamma is just going to be integral from 0 to infinity e raised to minus x times x to the n minus 1 times the natural log of x dx. And how does this evoke the question of finding the digamma function? That's because the digamma of, say, n is defined as the derivative with respect to n of the natural log of gamma of n. So by the chain rule, this is gamma prime of n divided by gamma of n. So gamma prime of n can just be written as digamma of n times gamma of n. So that's why for gamma prime of 1, we needed digamma of 1 times gamma of 1, which is 0 factorial, which is just 1. So we just ignore that. So digamma of 1 is gamma prime of 1. That's why. And one thing that I failed to point out in that video is the digamma symbol that I used, this one, is the commonly used mathematical notation. This is commonly used mathematical notation for the digamma. Or polygammas in general, you can have sub 2 to denote it's a digamma. You can have a trigamma when it's 3. So this is the commonly used modern notation, but in that video I have used this archaic notation for digamma, which appears in my logo and I think also the thumbnail of this video. So don't be discouraged if you don't understand what this is. This is equivalent to this. Okay, so with that being said, let's go on to calculate the digamma of 1. So since we know that gamma is this, gamma prime can just be found out as the integral from 0 to infinity of e raised to negative x times x to the n minus 1 times the natural log of x dx. This is just the chain rule, don't worry about that. But since we need to find gamma prime of 1, which I showed is equal to the digamma of 1, can be written as integral from 0 to infinity. In place of n, we just have to put 1. So e raised to negative x times x to the 1 minus 1 is 0 times natural log of x dx. This will go to 1. So we are left with integral from 0 to infinity of e raised to negative x times natural log of x dx. And we basically have to work with this integral to find the digamma of 1. And after this part was precisely what I couldn't calculate last year, but I finally can. I don't know, after being enlightened by some math techniques and stuff. I mean, you saw my content evolve, right, as I did. So it's like a milestone, this video, to my journey. So let's calculate this integral on a fresh page. See you there. Now we have this e raised to negative x, this exponential factor. Now I urge you to look at what e was. So e, in terms of limits, can be represented as the limit as n goes to infinity of 1 plus 1 over n to the nth power. This is just the definition of e, right? And I believe it was Euler who discovered e. That's why e is Euler's constant, e. You can also represent this in terms of limit going as n tends to 0 of 1 plus n raised to 1 over n. I'm just changing the limit. But we can also represent e raised to x, this variable, exponential variable, in terms of this first species with limit as n goes to infinity of 1 plus, and over here instead of this 1 we can have x over n to the n. This is a perfectly valid definition of e. You can look it up if you want. Now since we have e raised to negative x, let's make that change. E raised to negative x is limit as n goes to infinity of 1 minus x over n, all raised to the nth power. So I would really like to go ahead and plug this definition of e raised to negative x inside our integral. So we have digamma of 1 is equal to integral from 0 to infinity. But wait, before I forget, we have a limit. We have to take the limit outside the integral. Limit as n tends to infinity of the integral from 0 to infinity of, in place of e raised to negative x, we have 1 minus x over n to the nth power times natural log of x dx. Just in place of this, we plugged in the limit definition. Well, fair enough. Now one thing we can do, one great thing we can do, is introduce a substitution. So let u equal to 1 minus x over n. So du is naturally negative 1 over n times dx. Now here comes the slightly tricky part, the upper and lower bounds. So when x is 0, you have 1 minus 0, so u is 1, and when x tends to infinity, we can't let x equal infinity, that would just be bad notation. We let x tend to infinity. So when that happens, notice in this factor over here, we have a limit as x tends to infinity of 1 minus x over n. But for your kind information, we again have a simultaneous limit as n goes to infinity, which we also have to consider, because n is not just a single finite value. We also need to consider this fact. And you might say, like, although the limit is outside, how is it acting? It's because you can take the limit inside the integral, because we can assume convergence again. And moreover, if we temporarily forget this to the power n for now, because it's purely calculating the upper and lower bounds, we don't care about this n factor for now. Notice that both n go to infinity and x go to infinity simultaneously. So this is a simultaneous limit problem, and there is a rigorous way of dealing with this, which I'm not going to go into because it's well beyond my scope of knowledge, and you can really use the epsilon delta definition of the limit and figure out what the simultaneous limit goes to. But heuristically speaking, in this limit, n go to infinity, x go to infinity, it's almost like saying, this is almost like saying that limit as, say, another variable k go to infinity of 1 minus k over k. Because notice that both have the same form. X is not raised to any other power, n is not raised to any other power. We might as well consider them, and I'm not saying this is equal to, but we can consider them. This is like a squiggly inequality. We can consider them to be a same variable tending to infinity, such that this cancels out. So we are just left with 1 minus 1, which is 0. So heuristically speaking, as in the limit as x tends to infinity, the upper bound, basically u, will go to 0. So that's what was the tricky part about this the simultaneous limit problem, and that was actually posing a problem to us now, and we heuristically solved it out, and the final result actually proves that this heuristic approach was pretty accurate, if not perfectly correct. So just bear with me now if I'm less rigorous right now. So now, knowing these upper and lower bounds, we can just transform everything. So we have the digamma of 1 is equal to, still we have the limit outside, we can't ignore that. Limit as n goes to infinity of um, integral from 1 to 0 of u. Now 1 minus x to the n is u to the nth power times the natural log of, well, what is x? Un is equal to n minus x. So x is nothing but n times 1 minus u. So natural log of n times 1 minus u, and dx is now negative n du. So we can use the negative to flip the upper and lower bounds, correct the order of integration, and we can pull out these n terms because they don't depend on u. So limit as n goes to infinity of n times integral from 0 to 1. Now flipping it, we have u to the n and then natural log of n times 1 minus u du. Now I want to use a nice property of logs in general. So if you have log of a times b, which can be decomposed as natural log of a plus natural log of b. So this becomes limit as n goes to infinity of n times integral from 0 to 1 of u to the n times natural log of n plus natural log of 1 minus u du. So we can split this up into two integrals by linearity. So limit as n goes to infinity of n times integral from 0 to 1 of u to the n times natural log of n du plus limit as n goes to infinity of n times integral from 0 to 1 of u to the n times natural log of 1 minus u du. Well, we can pull the natural log of n outside because it does not depend on u. Limit as n goes to infinity of n times natural log of n and integral from 0 to 1 of u to the n du. And the second integral, we can use the Taylor expansion for the natural log. So notice that natural log of 1 plus x is equal to sum from k equals 1 to infinity of minus 1 to the k plus 1 over k times x to the k. So we have limit as n goes to infinity of n times sum from k equals 1 to infinity of minus 1 to the k plus 1 over k. And we also have, because of this negative u now, minus 1 to the k factors times integral from 0 to 1 of u to the n times u to the k du. So we can calculate this limit as n goes to infinity of n times natural log of n, and then antiderivative of this is u to the n plus 1 over n plus 1 evaluated from 0 to 1. And well, minus 1 to the k times minus 1 to the k is minus 1 to the 2k, which will be 1 because it's an even power. And so we just end up with minus 1 to the 1, which is minus limit as n goes to infinity of n times sum from k equals 1 to infinity of, well, integral from 0 to 1 of u to the n plus k du. And now evaluating this, we have limit as n goes to infinity of natural log of n, and when at plugging this in, 1 to the n plus 1 is 1, minus 0 is 0. So we just have 1, this n times 1 over n plus 1 minus the limit as n goes to infinity of, well, don't forget the 1 over k factor, really sorry about that, sum from k equals 1 to infinity of 1 over k, antiderivative is again easy, u to the n plus k plus 1 divided by n plus k plus 1 evaluated from 0 to 0 to 1. Now using the product properties of limits, we can split this up into two limits. So limit as n goes to infinity of natural log of n times limit as n goes to infinity of n over n plus 1 minus, calculating this is easy, so limit as n goes to infinity of sum from k equals 1 to infinity of, we have basically n in the numerator divided by k times n plus k plus 1, because times 1 basically, because of this we just don't write that now. So we can totally write this as limit as n goes to infinity of natural log of n times limit as n goes to infinity of, dividing by n, 1 over 1 plus 1 over n minus, I can take the limit inside, sum from k equals 1 to infinity of limit as n goes to infinity, again dividing by n both sides, numerator and denominator, we have 1 over k over n times 1 plus k over n plus 1 over n. So now as n goes to infinity, this term will go to 0. So 1 plus 0 is 1, 1 over 1 is 1, so this entire thing is 1. So we're left with limit as n goes to infinity of natural log of n minus. Now one thing worth noting is, since as long as k is some positive finite integer, the limit of as n tends to infinity is going to dominate. So all of these terms are going to cancel out essentially. So I'm sorry guys, I made a slight error. So when we are dividing by numerator and denominator, we only needed to divide this factor by n, because dividing this by n would mean that we divide by n squared. So we're not dividing this k. Now, as long as k is a finite positive value, positive integer, we don't have a problem because the limit is always going to dominate. So this term will go to 0, this term will go to 0, and we're just going to be left with this k. Fair enough. But for the last term, is it's going to look like limit as k goes to infinity of limit as n goes to infinity of 1 over k times 1 plus k over n plus 1 over n. So we have another simultaneous limit problem which I would like to do heuristically. And notice that since we have two k's over here, firstly let's just rewrite this quickly. We don't need those divided by n now. Just for this, we have limit as k goes to infinity and limit as n goes to infinity, and n over k times n plus k plus 1. So there's a tug of war between the numerator and denominator. The numerator wants to explode to infinity, and the denominator, because it has a k, will also want to explode to infinity. But you did not notice that there is not one k but two k's. So the aggregate power of the denominator is k squared. So although the numerator and denominator both will go to infinity, the denominator will go to infinity faster because of this k squared term, because this will be nk plus k squared plus k if you expand it. So because of this k squared term, this limit as k goes to infinity is going to dominate the upper limit. So as the denominator goes to infinity faster, the entire fraction goes to 0. So for the infinity case, because the entire simultaneous limit will go to 0, and for all other finite cases where k is not going to infinity, we are just left with 1 over k, right? Because all the other terms will just 1 plus 0 plus 0, so everything else is 1. So all we are left with is basically the sum from k equals 1 to infinity of 1 over k, because all the other terms just go to 0 in the limit, and there is also no problem at infinity if you were considering that. And now what does this look like? So if we take a minus out common, we have sum from k equals 1 to infinity of 1 over k minus limit as n goes to infinity of natural log of n. This is just the kth harmonic number, rather limit as n goes to infinity of h of nth harmonic number minus natural log of n. That's what this is. And what is this? By definition, Euler-Mascheroni constant. So this is just evaluates to minus Euler-Mascheroni constant, and this was basically our digamma of 1. So digamma of 1 is basically your Euler-Mascheroni constant, and that's what we had to show. It's a really satisfying conclusion. We did not use series representation for the digamma. Just use the definition of a gamma, and so we just solved it using this limit definition and everything. That's it for this video then. Okay, so please like, share, and subscribe to my channel. Recommend me to your friend, fellow mathematicians, number files, aficionados, anybody. I just want more subscribers. You can um, follow me on my Instagram channel, gamma_digamma. In the meantime, stay home, stay safe. Have a great day, and peace out.